why does Pascal's triangle work, and what does it have to do with combinations? Pascal's triangle is a recursive array following the rules n choose 0 equals n choose n equals 1, and n choose r equals n minus 1 choose r plus n minus 1 choose r minus 1, for 0 is less than r is less than n. N is equal to the number of the row starting with the 0th row, and r is the column in that row starting with the 0th column. Each number in Pascal's triangle is equal to the number of paths to reach that number from the top of the triangle by going down left or down right. In order to reach any number n choose r, you must go down right r times and down left n minus r times. Therefore, each number in Pascal's triangle is equal to the number of ways you can arrange a sequence of right r times and left n minus r times. Now that we know that the number of permutations for n items is n factorial, but all the lefts are the same and all the rights are the same. Therefore, to get the number of combinations, we divide the total number of permutations by the number of permutations for lefts and the number of permutations for rights. This gives us n choose r equals n factorial divided by a quantity of r factorial times n minus r factorial. Because of the way factorials work, this will always equal a whole number. N times n minus 1 is always divisible by 2. N times n minus 1 times n minus 2 is always divisible by 6. N times n minus 1 times n minus 2 times n minus 3 is always divisible by 24, and so on. Because no matter what number you start with, n or n minus 1 will always be divisible by 2. n minus 1 or n minus 2 will always be divisible by 3. n minus 1, n minus 2, or n minus 3 will always be divisible by 4, and so on. Now, there's nothing special about left and right. This method for finding combinations will work for any pair of choices. We can even use Pascal's triangle to generate the coefficients for any binomial a plus b to the n power equals n choose 0 times a to the n plus n choose 1 times a to the n minus 1 times b to the first plus n choose 2 times a to the n minus 2 times b to the 2 plus so on until we get to n choose n times b to the n. The distributive property of multiplication dictates that we have to add up every combination of n a's and b's, which gives us this distribution. Now, since the 0th row just has a 1 in it, and the sum of each row is double the previous row because we placed 2 1s in the ends, and all the numbers in the middle contribute to the sum twice, each row in Pascal's triangle sums to 2 to the n. This can be trivially demonstrated by substituting a equals 1 and b equals 1 into a plus b to the n. Now, each column in Pascal's triangle can also be used for combination numbers. The 0th row is always 1. The first column is the natural numbers. Second column is the triangular numbers. The third column is the tetrahedral numbers. And we can keep doing this up to any number of dimensions we like, but this gives us the most common geometric combinations. That's all for today. Remember to like, share, and subscribe, and leave any questions in the comments section. Thank you.